Hi, Rakshita from CSC AML Section C. My topic is AI System Resilience. Let's enter into the topic. Introduction to AI System Resilience. AI System Resilience refers to the ability of an AI system to maintain accessibility performance under adverse conditions such as data corruption, adversarial attacks, or hardware failures. Resilience is quantified using metrics like mean time between failures (MTBT) and recovery time objective (RTO), adapted from traditional fault to tolerant system. Unlike robustness, which focuses on performance under noise, resilience emphasizes recovery and continuity of service after disruption. Resilience AI systems must integrate redundancy, grateful regression, and self-healing mechanisms at both algorithmic and architectural levels. In safety critical domains like autonomous aviation, resilience is not optional. It is requirement enforced by regulatory standards such as DO 178C and ARP 4754A. Threat models in AI systems. Adversarial examples are inputs perturbed by small imperceptible noise such that causing misclassifications. F of x plus tau not equals to f of x. Data poisoning attacks inject malicious training samples to manipulate model behavior, often modeled as optimizing a loss function with injected outliers. Model inversion and membership inference attacks exploit model outputs to reconstruct training data or infer participation, violating privacy. Backdoor attacks embed triggers during training so that models behave normally on clean inputs but misclassify when the triggers is present. Hardware level threats include bit flip attacks on GPU memory, modeled as default injection in tensor computations T dash equals to TF, where F is fault mask. Fault tolerance in neural networks. Neural networks exhibit inherent fault tolerance due to distributed representations where localized neuron failures have minimal impact on overall output. Redundancy can be introduced via ensemble methods where final prediction is y equals to 1 by n sigma I fi of x, improving resilience through voting or averaging. Checkpointing and rollback recovery allow systems to restore to a prior state after failure. Using periodic snapshots of model weights and optimizer states, correcting codes (ECC) can be applied to weight matrices to detect and correct bit errors during inference, especially in edge deployments. The resilience of a network can be analyzed using sensitivity matrix dou y by dou w, measuring output change per weight perturbation. Adversarial robustness and defenses. Adversarial training minimizes the worst case loss. Minimum 0 EXY max down, enhancing model robustness against perturbations. Defensive distillation trains a model to output softened probabilities, reducing gradient magnitude and making attacks harder to craft. Randomized smoothing certifies robustness by adding Gaussian noise during inference and using majority voting over noisy samples. Certified defenses provide formal guarantees. For input x, if x minus x dash square less than r, then prediction remains unchanged with high probability. Trade-offs exist between accuracy and robustness. Robust models often exhibit lower clean accuracy due to regularization effects. Runtime monitoring and anomaly detection. Runtime monitoring monitors analyze model inputs and outputs using statistics test. Example, Kolmogorov Smirnov to detect distributional shifts. Autoencoders can reconstruct inputs. High reconstruction error indicates anomalous behavior, triggering alerts or fallback models. Monitoring systems must balance sensitivity and false alarm rates, often turned using receiver operating characteristics ROC curves. Self-healing systems use feedback loops to detect degradation and initiate recovery, such as retraining on new data or switching to backup models. Rollback recovery restores system state from checkpoints using versioned model weights stored in distributed storage. Example S3 HDFS. Dynamic reconfiguration allows switching between models based on performance metrics using policies defined by Markov Decision Process (MDPS). Online learning enables continuous model updates. Theta t plus 1 equals to theta t minus n delta L theta t xt yt. Adapting to concept drift while maintaining stability. Recovery time is minimized through warm starting, where new models are initialized from previous weights to accelerate cover rates. Formal verification of AI systems. Formal verification using mathematical methods to prove that an AI system satisfies safety properties under bounded perturbation. Reachability analysis computes all possible outputs of a neutral network given input bounds using tools like Reluplex or Marabou. Probabilistics model checking verifies temporal logic properties, example PCTR, on stochastic AI systems such as Markov decision process. Verification scales poorly with network size abstraction techniques, example layer merging, activation clustering, reduce complexity, reliance in distribution and edge AI. Edge AI systems use model compression, example quantization pruning, to maintain functionality under resource constraints or partial failures. Latency and bandwidth constraints require resilient communication protocols with retransmission and error correction. Example TCP FEC. Energy aware resilience prioritizes critical model components during power outages using dynamic voltage and frequency scaling DBFS. This was a case study of resilience autopilot AI in aviation. Metrics and evaluation of AI resilience. Resilience is measured using metrics like resilience capacity RC equals to integration P of T dt, where P of T is performance over time post disruption. Mean time to recover MTTR qualifies average recovery duration, critical for real-time systems with strict deadlines. Robustness, accuracy trade-off, curves plot clean accuracy versus adversarial accuracy under increasing sigma guiding model selection. Simulation-based evaluation uses digital twins to stress test AI systems under synthetic but realistic fault scenarios. Future directions and research challenges. Few research challenges out there. Quantum inspired resilience models explore in entanglement and superposition for fault tolerant distribution AI computation. Cross distribution collaboration with aerospace, cybersecurity, and control theory is essential for next generation resilient AI. Thank you. Thank you.